Perfect. All right, then let's start. First, I want to introduce myself. My name is Uwe Popp. I studied material science and engineering in the Max Planck Institute, affiliated with the University of Stuttgart in Germany. And I had the opportunity to work with Apium now for 3.5 years, and it's a very interesting journey so far. We had a lot of adventures to come to this point of processing PEEK. And today I want to talk with you about the following points. First of all, I want to give an introduction of PEEK, about the material characteristics. I want to highlight some advantages and disadvantages. In the next chapter, I want to speak about applications for different requirements. Here I want to refer to example parts of additive manufactured PEEK. I think this might be very useful for most of you to get an idea and to get already inspiration where additive manufacturing and high-performance polymers are already used and can be used and have and can be very beneficial for you, your company, or your research. I also want to highlight composite materials of PEEK. This is also something we have been looking into. And here we also have a lot of interesting properties where we can use PEEK composite materials. The next chapter then is challenges and opportunities of FFF PEEK printing. So the ones of you that have already printed PEEK or have some experience with this polymer, with polyether-ether ketone, know that it's not so easy to process these materials. And there are some things one has to keep in mind when it comes to work with this kind of polymer or thermoplastic. And I want to hint and highlight some of the necessary considerations one has to take when it comes to work with this polymer. Therefore, I will be talking about the morphology and crystalline architecture of the polymer to get an understanding what it will be. I will highlight also the benefits of FFF PEEK printing. And in the end, I want to show you some material tests and results we did in regards to the layer adhesion. And as a final point, I want to remark storage conditions of this polymer. After that, I would propose we can have a summary and question round where you can ask questions that have occurred during this presentation. Feel free to ask the questions. I would say we do it about 10 to 15 minutes. And then in the end, I would be happy if you could participate in our question round so we can get some kind of feedback. But this we will do at the very last point. All right. So what are the key learnings from today? What is important to me is that we get an understanding of the semi-crystalline nature of PEEK. I also want to show you the applicability of PEEK and its composites and the properties of additive manufactured PEEK parts. PEEK is a very interesting thermoplastic polymer, and when we are looking at the pyramid of thermoplastic materials, we can see it is located at a top position of this pyramid. So this pyramid is in principle divided into two sections. On the left side, we see amorphous polymers like PI, polyether imide, PPSU, also high temperature thermoplastics, very interesting in nature. On the right side, we have PEEK, and its composites. We also see polymers like PVDF, which is also very interesting in terms of chemical properties. And the more we go up this pyramid, the higher is the thermal resistivity, the higher is the mechanical resistance, and so on and so on. So what makes PEEK a very special polymer is it is at first a semi-crystalline thermoplastic. Therefore, it has high fatigue strength and ductility. Like all thermoplastic, it is a good vibration and noise reduction material to work with. So due to the amorphous part that is still in the polymer, we have a lot of energy dumping opportunities. We also have the chemical resistance of the material, so it is resistance against most of the acids and bases. For halogenic acids, we see that this material is not resistant. Also for sulfuric acid, this material will get damaged. It also has a high wear resistance, so we can find PEEK already used in bearings, for example, or when we think of medical applications, we can already see PEEK used in knee implants, for example. Therefore, we have excellent friction behavior. This goes one by one, so we have a high resistivity when it comes to friction when we have the right counterbody. This is important to mention. We have high dielectric strength and stiffness, and as well a high stress crack resistance. What makes PEEK also very interesting and good to use is it's tolerant against gamma radiation. This is something we have to consider when it comes to sterilization processes, for example. So there's the opportunity to sterilize PEEK by gamma radiation, and PEEK won't degrade too much. We once even got a very interesting call from the CERN center, where they were doing all kind of testings, and they are working with high energy radiation, and they had a keen interest in PEEK because it didn't degrade too much, and also showed a lot of interesting properties, for example, being non-magnetic, but also resistant to high temperatures. We also have excellent flame retardancy. This is very interesting in terms of aerospace application. So PEEK won't start to burn itself, it will rather melt, and don't add additional energy when it comes to a fire. Then it's a very good isolator in case of extreme or hot temperatures. It also has good osseointegration is something we have to be careful about, because this also is dependent on the surface. In nature, PEEK is more chemically inert, so this means it won't react with any other materials. But it can be good for osseointegrations if you have surfaces where cells can adhere or bone could grow into. We have a wide thermal operation range, so we can have PEEK parts that are operating in elevated temperatures. There's also the short time usage of 260 degrees when it can be used without seeing a lot of plastic deformation, but this is then more done for very short application when there's not too much load on the part. PEEK can also operate in harsh environments. So as said before, it is chemically inert, and we could think of PEEK used, for example, in the oil and gas sector. There we have seen PEEK already used when they do these gas explosions to check for new oil reservoirs. I mean, this is the normal procedure in the oil and gas sector. When you're looking for new fields of oil, you drill a hole and get some kind of a probe down this hole, and there's a gas explosion, and with the seismic waves you can check, okay, where is some liquid storage or not. And PEEK is one of the materials that is used for this application, because we have high temperatures, high pressure, and PEEK is resistant to these environmental conditions. PEEK also has a long life cycle, so it's fairly resistant against outer influences. And lightweight construction is possible because we have a very low density of 1.34 gram per cubic centimeters, which makes it very attractive when we think of applications where we have lower fuel consumption. Then disadvantages of PEEK. When we think of working with PEEK, we need a lot of knowledge how this material will be treated, especially in an FFF fashion, to get very good parts. Also, when you think of milling, you also need to know how to work with the material. There are inner stresses built up when it comes to the extrusion of stock shape material, and even if you mill, you have to consider changing the position when it is fixed on the machine, because it will eventually warp. It is a high-priced polymer as well, and we have high material waste with traditional manufacturing methods. So here on the right side, we see an image of the process. I want to highlight it once more to get a better understanding how the FFF process is working. And here we had a short video of processing PEEK with our machines. We can see our machine here, some example parts displayed with carbon fiber reinforced PEEK. And yeah, this is where the process starts. And as you can see, it's a layer by layer build up where hot material gets extruded out of the nozzle and is deposited on the previous layer. I will speak later a bit more about why we have these two plate systems, what kind of benefit we have from it, how the material is treated in a different way by using this methodology. Exactly. Yeah, we can have complex geometries built as we see here. So things that are in a traditional way hard to manufacture. All right. So we continue. Advantages, what we have with FFF processing. We have, of course, material savings. So we only deposit what is needed. In the end, we can have very few material waste when we think of the brim that has to be taken off. We can also have on-demand production, functional prototyping, since the material properties that will come out of the print show already the right mechanical performances. If you think of the load case, this part will later be exposed to. We have fairly low acquisition and production cost compared to other manufacturing methods. We are quite free in design, which I think is a very good advantage. So complex parts can easily be produced, especially organic structures, when we think of implants which would be created. It's a good research and development tool. Here we also saw very interesting requests from customers. Whenever you need the temperature resistance, you need, for example, transparency for different research sensors when it comes to either CT scan or when we have radiation you want to check for. And it is also non-magnetic. So it is a good way to make parts that will hold samples and you don't want to use metal. Or when you think of biology and you can have some kind of reactor system, then it is also very beneficial because it is mostly chemically inert to all kinds of chemicals. And the last point we see is the low maintenance cost. So the tool which you're using is in principle just a nozzle. This can be exchanged from time to time, and that's basically it about maintenance. Maybe in our case, check for cooling fluid. Yeah, but so far you have very low maintenance cost. The challenges we have when it comes to FFF PEEK printing, what we want to have, or I think you too, is high print quality and smooth surfaces, no black specks. So these black specks is some kind of a vitrification that takes place when the material is exposed to high temperatures for too long time. We will get some kind of chemical degradation, and this will appear in some kind of black specks. So this is something you want to avoid because it doesn't have the same mechanical properties or properties at all than the PEEK that is wanted. High reproducibility. Here we have to be careful what we are talking about because this is mainly dependent on the G-code that is created. So whenever you make a new G-code, your reproducibility will change. But if you take the same G-code over and over again, the reproducibility is quite high. Warping of parts. So here we have to also understand the nature of the polymer to see what would be a very beneficial geometry to work with to avoid warping as much as possible. When we think of milling, we mostly talk of parts that are also fit for being machined. So whenever it comes to the construction of different parts, you construct them always having in mind how you want to machine them later. And this kind of thinking also needs to be done when it comes to FFF printing. And this is something very critical and is mostly overseen by the people that are applying FFF processes and think still of parts that will later be machined. Then geometry, size and overhangs. We cannot print everything. This is something we have to say. But there are some organic things or organic structures or other structures that are otherwise hard to make, which can be processed very well with this technology. Support material is something that is also a critical point. We are still working on something that we can have a good solution to get rid of support material. For now, we are still using PEEK as a support for PEEK. Because of the high temperatures that are used, we don't know another material that can withstand the temperatures and still be a supportive material when it comes to overhangs. So what I said in these challenges is you have to think of the way you want to process the material later, but you also have to think of the load case the part will be exposed later. And this is something a lot of people have had a look at it. And also when we are giving trainings, we also offer trainings and design for 3D printing. We are also highlighting and teaching when it comes to the creation of parts being optimized for FFF printing. So what we can see on this image here is a load case of an L-shaped part, and the load is taking place at the upper part indicated by the arrows. The color change indicates where the highest stresses are working. And here we see the first part where we can do something with FFF printing. So the corner here at the top left part is a 90-degree corner. And we see with the top right part, if we smoothen out this corner, that we don't have 90 degrees, but a smooth transition from these perpendicular surfaces, we can already see a decrease in stress that is working and therefore a higher part performance. And this smoothening of the transition is something that can be easily achieved with FFF printing. Or if you think one step further, so from the lower left, which is the same image as the top left, to the lower right image, we see this big hole in the middle, and we see hardly any more stress. And with thinking or with ideas like this, how parts can be changed dependent on the load case without taking more material, because I think the material that is used is here the same. We can have even a better part performance when we know the load case and when we know what to do within FFF printing. When we compare the mechanical properties of PEEK in terms of the different manufacturing methods, we see that with FFF printing we can achieve the same properties like injection molded when we place this part in the XY plane. So when we think of the part before and we would lay it down on the print bed, would print it out, we can have a part that is performing like an injection molded part. But when we also apply the thinking of the load case construction, we can have a very good part that is performing very well. Yeah, now I want to come to example parts in additive manufacturing, where we have already done some kind of applications. You see different examples, for as we see here, a drive gear system in the automotive sector, or some sealings when it comes to the oil and gas sector, as I said before. When we think of exposure to crude oil or harsh environments, then this material is very well to be used. We can also have lightweight applications like the lightweight angle and a cheekbone implant as we see it on the top right. So the medical sector is something we are focusing on, and we want to go there very soon because we see here the highest demand for mass customization products. What is also a very interesting field is the mold making, and this is something I want to highlight with the next slide. Then also semiconductors and electronics, functional prototyping and research and development parts, all kind of different things. Mold making is something that we thought about. We have a material that is wear resistant, that can be exposed to elevated temperatures. And we know that mold making is a very cost-intensive procedure. So we were thinking why we are not doing molds out of PEEK for other polymers. And we actually had the opportunity to look into this with LEM Technics. And they made molds to make these kind of screws and dampers. And what is very interesting and what I want to show you is the cost savings that was achieved by using molds manufactured with PEEK and FFF printing over conventional manufacturing. And so LEM Technics were kind enough to give us some kind of calculation we are free to share with you. So when they were looking at the different steps that need to be done to create this mold, they said it takes in Bulgaria about 90 euros and in Central Europe about 200 euros in a day for the insert preparation. Electrode milling takes another day and 660 euros in Central Europe. The milling shape 1,600 euros per 2 days. The CAM programming 480 euros and 1 day in Central Europe, and the eroding of the ribs 280 euros and 1 day, which leads to a total manufacturing cost of 3,220 euros in Central Europe, or almost half of it in Bulgaria. But you take 6 days until this is done. And in comparison, what they did when it comes to FFF printing, it was only 1 second. Seems to be loading here. They did a model preparation, which cost them half a day and about 250 euros in Central Europe. Printing, 77 euros in 1 day, and a post-processing, a third of a day and 120 euros, which comes to a manufacturing cost in Central Europe of 450 euros, which is approximately 1/8 of the price we've seen before with the conventional method, and only 2 days. So not only you save on cost, but also on time when it comes to the manufacturing of it. We also looked in other opportunities we could do with this kind of technology, and we also have seen topology optimization. So we had this bearing seat, which we thought of conventional manufacturing and in topology optimizing. And then we did some kind of comparison. How much would it cost us with different technologies to make the bearing seat on the left side? And how much would it cost us to make the topology optimized seat on the right side? And how much time it would take as well. And therefore you see a table which is basically comparing the costs. On the left side, we see different technologies, SLS, PolyJet, SLA, FDM, with also different materials for the conventional seat. And on the right side, we compared it with the topology optimized seat. The only thing on this table which is a bit not satisfying is we couldn't compare milling, because nobody wanted to mill the topology optimized bearing seat. But long story short, what we can see here on the right side is the FFF printing of PEEK of this topology optimized seat is only half the cost, which means this topology optimization is not only material saving, but is also cost saving for most of the applications. This is the basic outline of this comparison. In the end, we also created this part, and the outcome was this. This is the topology optimized seat, and as you can see here, this is not PEEK, but it is a composite material. So we printed it already with carbon fiber reinforced PEEK. So carbon fiber reinforced PEEK is not only very interesting when it comes to mechanical applications, but it is also very interesting when it comes to thermal applications. And herefore we were thinking about the mold we have seen before, and we did a comparison in thermal conductivity. And what we can clearly see is that carbon PEEK has a way better thermal conductivity than regular PEEK. And therefore we thought carbon PEEK could be a very interesting material when it comes to mold making. Just give me a short break, I will take a sip of water. Yeah, I've spoken about, a lot about PEEK and the composites just a bit, and the very interesting part is how we process this material. So of course we did a lot of thinking in processing PEEK and other high-performance thermoplastics, and what makes our machine very special is the adaptive heating system, where we bring in the needed heat for the part to come to its thermodynamic equilibrium state. What we also did is we did a lot of engineering on the extruder technology, because the extruder plays also a critical role within this complete workflow. We have to make sure that the same amount of material is all the time extruded as we want to have it. We have Apm Control Software, so we have a data storage where we have stored most of the critical parameters that are needed to work with the material in the best case. So as it is highlighted here, the crystallization behavior of PEEK. Yeah, and the outline here, that in order to create the best parts, you need, of course, a very good tool to be able to process the material in its best way. Just a short reminder how our technology is working. This is really just a short look into it. So we have the CAD model, and out of this we create a toolpath, you know, the G code. And this G code is telling the printhead where to deposit the material. We have this layer-wise build-up, and in the end we get the finished product. But in the layer-wise build-up is where all the technological ideas and the engineering is hidden, basically, when we think of the semi-crystalline nature of the polymer. When we're looking at the molecular structure of this material, we can clearly see that we have amorphous regions and we have crystalline regions. The crystalline regions are mainly responsible for the high mechanical performance, whereas the amorphous regions are mainly responsible when it comes to, for example, this noise reduction or damping system, or when we think of the elastic behavior or plastic behavior. And what I want to highlight as well on the right side is you see two different images of crystallization processes. So when we think of a melt and then crystallize it, we have in principle two different crystallization mechanisms. Either we have a homogeneous crystallization, as we see here on the top right part, where statistically at certain positions the crystals start to form and to grow, and then we have a globular growth, which is also the growth, the preferred growth mechanism of PEEK. And on the image below we can see a heterogeneous crystallization growth, where we have already a site where crystals have been formed before, and then the next crystals will start to crystallize on these already existing surfaces because it takes less energy. And this is something we see also within our crystallization process when we deposit always a new molten layer on an already existing surface. So again, the crystalline structure is very critical. So we have the thermodynamic equilibrium, we have the formation of the crystalline lamella. And why do we need it so badly? When we are looking at a tensile test, so we are loading the part in a tensile mode. As you can see here, we start from the crystalline in the amorphous regions, and then we apply forces. The first thing that happens is the amorphous regions will start to expand, they will start to untangle, and this is where we see a very few resistance, and we have the first plastic deformation. This can be either in the elastic way, or then if we detangle more and more, it will be in the plastic way. And then comes the crystalline parts into play when the polymer chains in the amorphous regions cannot be stretched anymore. The crystals start to slightly shift according to Schmidt's law, but I think this is too deep into the material science. But what we see then here is that different planes are starting to slip next to each other, and this is where we have the highest mechanical resistance of the part until it comes to the fracture of the crystalline structures, and this is where the part then finally breaks. So what I want to highlight here is that the semi-crystalline nature, and especially deformation of the crystalline phase, is absolutely key when it comes to the material performance of the parts. And this is where our technology is in principle working. So when we see here over time the temperature, the material that is deposited sees, we bring it in our hot end or in our printhead into the melt stage. This is where you see here the hot end. Then we deposit it, it already cools down. We see the formation of crystals, and then with the plate on top, the zone heater, and a plate that comes together with zone heater, hot and the heating bed. We keep it at an elevated temperature, so we give the materials enough time to come to the equilibrium state, and then we cool it down to room temperature. And this is critical because if this is not done properly, the layers won't adhere too well together. And this is something we have already seen when we did several tests, for example, Charpy tests. And of course, rotation of the part plays a critical role, but also here the layers were breaking itself. This is not what we wanted to see. What we wanted to see was on the top, on the bottom left side of the part, where you see a crack propagating through the layers. And then we can say we have very good layer adhesion. But if we don't have this kind of layer adhesion, we can already see, for example, on the right side, the Charpy tests where they have been hit through in the middle. We can see that the layers were just breaking by itself. And layer adhesion is something we are looking deeply into this topic. So what we've done just recently was we have been comparing different suppliers for PEEK material and did internal testing, mainly on 3-point bending tests. And we could see there's a lot of difference for the PEEK grades that are existing in the market. And this is something we will explore further. So we see different stress resistance, we see different Young's modulus in bend mode, and some materials perform better than others. This is also dependent on the molecular weight of the materials. So the ones that have a lower molecular weight, they tend to crystallize faster, but also you see in mechanical performance, they perform lower. So the ones with the fewer values in bending resistance, these are the values you see on the right side of the table. These are the ones with a low molecular weight. They have also less warping, but also less mechanical performance. The last point I want to tell you about is the storage conditions. So this is something very critical because PEEK is in nature hygroscopic. It tends to attach water on the surface. I think this is normal for most of the polymers, and therefore you need to make sure that the material is always in a dried state. So either you dry it before and then use it, but within a day it will absorb a lot of moisture, or you use some kind of device where you can keep the material at elevated temperatures so moisture won't attach, and you have a dry filament. If you do not have a dry filament, you can already see at the nozzle the formation of bubbles, and therefore you will have less material extruded out. The extrusion is not constant. You will face holes and voids inside of your part. Our strategy to overcome this is we offer right now drying systems that can be placed next to our printer, and therefore we make sure that the material that comes into the printer is already dried, and you have a very good part that comes out in the end. It is also very beneficial for the set layer adhesion. A last hint, we have a service center in our company where we are happy to help you out. We offer trainings. We will also have soon interactive online trainings like this click meeting here, which we are offering now from time to time. If you're interested in it, kindly feel invited to contact our service center. We will share with you the knowledge and the know-how for processes we have acquired so far. And with this, I was speaking already 40 minutes. And now I think it's time for the question round. And I will have a look at the chat to see what kind of questions you've already placed here. All right. Can you write the answer to me? What is the hydrophilicity of our PEEK black? PEEK black is PEEK that is compounded with, what's the right word for it? So basically it's a coloring that is attached to it, and the hydrophilicity should be the same than for the neat PEEK. Okay, more questions. Do you consider the control of the crystallinity of the PEEK during the whole process as a challenge? If not, how do you control it? I hope I have already answered this question during my presentation with the play of the zone heater, the heating bed, and the nozzle. So these temperatures all together play a critical role for the crystallization. I've heard that PEEK is much easier to print compared to PEEK. What is the difference between PEEK and PEEK? Are you working on PEEK? PEEK is something we have already had a look to, that's true. But PEEK normally is even melting at higher temperatures and also has higher mechanical resistance in this case. At the point we were looking at it, it was even more challenging than PEEK for us. PEEK is in principle from the molecular structure one more ketone group instead of an ether group, and therefore it becomes more rigid or more resistant to plastic deformation. But PEEK is something we have on our list to look into. Right now it's nothing we are working on at the moment, but it's something we will have a look into definitely. Do you use a normalized tensile strength test, especially in Z direction? Yeah, Z direction is always critical, especially for the tensile test if we think of the printing of the tensile test. Because when we start to print and we go up and up and up, we have created some kind of a leverage. And sometimes we see that by applying the next layer, we also drag on top of the surface, and therefore the material is likely to bend over, and yeah, then the print is done basically. There are some ideas of using different support structures that we can have a higher resistance against leverage. What we are looking for now into the Z direction is in principle in 3-point bending tests, because we think we can also stress the part on the layers themselves and also get a good feedback on the Z layer adhesion. Are you looking at PEKEKK to print as well? I have to admit for now we are not looking into PEKEKK at the moment. I would not know who's already offering some kind of filament like this. It is something with our print head that would be possible to be processed. I'm pretty sure it could be processed. If you have some kind of filament or kind of interest in it, you are invited to get in contact with us and we can see what we can do there. Yeah. Any further questions from your side? I would be glad to answer some more questions. There's a question coming in. Or two questions. It's going to be quite some text. I mean, in any case, if you have questions on your mind coming up later, feel free to write us an email. This is also possible. Do you have feedbacks on SLS printing of PEEK? So far, what we have seen for SLS printing, since it's a sintering process, we always have more holes inside. It is more porous in nature, but this comes from the process itself. And therefore, we have seen that in mechanical performance, it performs in principle a bit weaker than in FFF or injection molded, but this comes simply from the process itself. How do you handle a reproducible process regarding the cooling times? The cooling times, for instance, will change between a big part and a small part. This is right. This is something we are still working on. As I said before, we have a database inside of our printer where we already have a cooling, how would I name it? A cooling process where we already have some experience that after the print we do some kind of a heat treatment, but you're right, for bigger parts it is different than for smaller parts. And therefore it's something we're looking into in a design of experiment. So we're trying out different options to increase our data storage on this. Okay, at the moment the price of PEEK is around 600 to 800 euros per kilo. Do you see any trend in price development of PEEK? Yeah, PEEK is in filament form very important, very expensive. Sorry, very expensive. I agree totally with you. The important part here is this all comes together with requests for it. So if we think how much material is sold in granular form and how much material is sold in filament form, it's only a question of how many people are asking for it. So if we are able to develop this technology further and to spread it further globally, then the price for PEEK filament will drop. I'm very sure about this. The building room has to be heated, right? Not necessarily. What needs to be done is to give the material enough energy, in which form ever, it doesn't matter, to be able to come to its equilibrium state at room temperature. You can either do this by just heating up everything, or you can do it by imposing enough energy that the part needs to come to its full crystallization. So you could either do it by radiation, you could either do it by convection, or whatever comes to your mind. The most important thing is that the material has enough time and energy to come to its final and stable state. All right, so I think the 10 minutes question round is over. As I said before, whenever you have a question, feel invited to write us an email. We are happy to answer it for you. And what I would like to ask you is to take part at our question round. And therefore, thank you very much for the attention. And I hope I could share some knowledge with you and it helped you in working with PEEK.